let's proceed to some further investigation of annuities. What we really need to find now is a payment for an annuity and also term for an annuity. We'll start with finding payment for an annuity. That's pretty much a straightforward process, but we'll see how this works. So we'll use this problem to investigate how we should go about finding payment for an annuity. So James took a loan of $20,000. It will take him 5 years to pay off the loan if the rate is 8% compounded monthly and if he pays the same payment at the end of every month. How much is his payment? So we don't know the payment now. What we know is that the loan amount is $20,000, so that's the present value of the annuity because that's the loan amount. Now we also know that this annuity is ordinary because the payment is made at the end of every month. Also we know that this annuity is simple, right? So it's compounded monthly for our rate, and also the payments are every month. So that makes annuity simple. So it is ordinary simple annuity, and we have present value for that annuity. Well, what this means is that $20,000 being the present value should be equal to PMT, the payment which we don't know, multiplied by 1 minus 1 plus 0.08 divided by 12 minus 12 times 5. Minus 12 times 5 because that's payments made every month for 5 years, and we also divide by 0.08 divided by 12. Okay. Now we just basically wrote down here the formula for present value of ordinary simple annuity. Now we need to find PMT. Well, as you can now probably already guess, that's a straightforward thing to do. So let's compute this. This will be some number A, and later we'll compute PMT. So PMT will be simply 20,000 divided by this number A. Okay, so let's compute this A, and let's use that A in this calculation. Okay, we'll go ahead and do that. Computing this A, if you compute this part, so this A, now I'll just write it down as, it will be 49.31843334. Okay, so we found this A. So this A is equal to 49.3184334. So now we'll do that. We'll find PMT from here. So we'll take $20,000 and divide by this A. So it's 405.53. So that's how we find payment for an annuity. Pretty straightforward process. But let's consider one more example just to make sure that we capture this process very well. So this problem asks, how much money should you pay at the beginning of every 3 months into an account earning 4.5% compounded monthly if you want to accumulate $60,000 at the end of 7 years? Okay, so this annuity is general, right? Because it's 4.5% compounded monthly for the rate, but the payments are made at the beginning of every 3 months, so 4 times per year, right? Quarterly. That's why this annuity is general, and also because we have payments happening at the beginning, this annuity is due. So there is a due general annuity. Now, that is the question about future value. We want to accumulate $60,000. But first we start with I2 because it's a general annuity. So we need to convert our rate. So we will have 5 divided by 12. Exponent will be 12 over 4 minus 1, right? So we convert this compounded monthly rate into compounded quarterly rate. So this I2 is 0.011292224. So that's I2. With this I2, annuity becomes simple annuity. Now we will need to find payment. But in order to find payment, we build our equation for the future value. So this $60,000 is the future value. We have payment, PMT, which we don't know, right? We don't know this payment. 1 plus I2. We have 4 times 7, right? 4 times 7 is our exponent, minus 1 I2. That's just the formula for future value. Also 1 plus I2. Why? Because that's a due annuity as well, right? If it's a due annuity, we need to multiply by this 1 plus I2. Now we will, denote this as our A. We'll compute this A. It will be the same process, after which we'll find PMT. So PMT will be $60,000 divided by this A. Okay, so this A is equal to PMT times 33.08680,942. Okay. So now we execute this thing. So we divide 60,000 by this number. Remember, don't round anything until you reach the final destination. So PMT is equal to 1,813.41. 8,813.41. That's our payment for this problem. As you can see, it is pretty straightforward to find payment. Let's now proceed to speaking about finding term for an annuity. Finding term will depend on whether you have future value or present value to start with. Okay, so let me show you how you would get a formula for term if you start with future value. Then I'll just tell you the formula for present value, and you will be able to verify for yourself that that formula for present value works, okay? And later we'll consider various examples. So let's start with future value formula for an annuity. So if you have future value for ordinary simple annuity, so that will be PMT 1 plus I n minus 1 I, right? So that will be the future value formula. Now if you want to get to that I, you will need to do some algebra, right? So future value will be divided by PMT. Then you will need to multiply that by I, just because there is division here by yi. So first you divide by PMT, then you multiply by this I, right? Then you move this 1 to the left side, so it's -1 here, it will become +1 there. So it will be 1 plus I n, okay? So after some algebra, you will achieve this. Then what you need to do is simply use logarithm power rule, which we already discussed when we talked about finding term for regular investments. So if you want to review that part, please go ahead and watch that class. So we will use logarithm on both sides. Basically, logarithm on this side, and because in an equation we should always repeat the same process on both sides to keep this equality. So after we use logarithm rule will work, and what it means is that this logarithm will be equal to n times logarithm 1 plus I. Well, which leads us to getting the formula for n. N will be the ratio of logarithm 1 plus, let me just move this 1 plus to this side. It doesn't matter because a plus b is b plus a, right? So plus future value times I divided by PMT and divided by logarithm 1 plus I. So that's the important formula for finding n when you have future value of annuity. So this formula is derived from the original future value formula with using of some algebra and also power rule of logarithms. If you didn't completely understand how we got here, it doesn't really, mean that you will be unsuccessful in the course. You can still use this formula without knowing how this formula actually was obtained, but it is always beneficial to know how to get this, because if you don't have access to a formula, you can always reproduce it. Now, just an exercise for you, maybe, is to try to get the formula for present value. So if you do the same kind of process, you will be able to get a formula for present value. You will be able to get a formula for n based on the present value of annuity. So that will be minus in front of the ratio. So then will be a logarithm 1 minus present value times I divided by PMT divided by logarithm 1 plus I. So that will be the formula for finding term when you start with present value of annuity. So they are very similar but also very different, right? So you have plus here and also you have plus here in front of ratio, right? So we just don't write it, but it's positive. But here in when you have present value, not only you have present value inside the formula, but also you have negative sign here in front and also negative in front of the ratio. Okay, let's go ahead now and consider an example of how we should use these formulas in applications. Consider this problem. How many payments are necessary to collect $10,000 if you pay $1,000 at the end of every year at 5% compounded annually? Okay, so that's a pretty straightforward problem, but there are some interesting things to discuss actually in this problem. So if you look at these formulas give you n, but what does that n mean? Okay, so that n means the number of payments. So remember that, that's very important. So this n means in these formulas the number of payments, okay? But in order to really deeply appreciate what that really means, we need to consider various examples surrounding this topic. So in this case, we know that annuity is ordinary simple because the rate is compounded annually and the payments are every year, and also the payments are at the end of every year. So that annuity is ordinary simple, which means that we can use one of those formulas. Namely, we will be using future value formula because we're collecting $10,000, which is the future value. Okay, so we'll be using this formula, and the reason why we can use it, because these formulas are based on those future value and present value formulas, which are valid for any ordinary simple annuity. If this annuity was not ordinary simple, we would have to make some modifications. For example, if that was a general annuity, we would change the rate, and if it was a due annuity, we would have to multiply payment by 1 plus I. But more about that later. For now, that's ordinary simple annuity. So we'll be using this N. Okay, so this will be again 1 plus future value is $10,000 times 0.05, because that rate I in this case is 5%. Nominal rate and periodic rate coincide because that's compounded annually rate. So we divide it by 1,000 and we divide by 1 plus 0.05. Okay, so we will calculate that. It will give us, so the result is 8.310386223. Now, because N gives us the number of payments, we see that there will be 8 whole payments and some partial payment will be also required in this problem. Okay? In total, there are 9 payments. So the answer to this problem is 9 payments. More detailed answer is 8 whole payments and 1 partial payment. So that's the answer. If this, you see this problem, how many payments are there necessary to collect $10,000? Answer is 9 payments are required. 8 whole payments and 1 partial payment. Okay, having said that, there is an interesting subtlety here. Okay, so it sometimes happens that that last partial payment actually can be a negative payment, which means that that last payment maybe is the one that not you are going to give to the bank, but also already the bank has to refund you that payment. Okay, so what that really means is that sometimes 8 whole payments will be enough for you to collect that necessary amount. So how that works is what we're going to talk now about, and that's very interesting. Okay, so we remember that it's going to be 9 payments, which is 8 whole, right, and 1 partial. So that's how we, that's based on our solution. So now let's investigate this partial part a little bit further. Okay. Now, what does that mean to have 8 whole payments? It means that after these 8 payments, you will still require to make some other payment, or maybe, as I already mentioned, bank will have to make that last payment to you. In order to find that out, what will happen after 8 whole payments, let's find future value after 8 whole payments. So future value of $1,000 which is paid for 8 years, because now I'm investigating what happens after 8 whole payments, right? So $1,000 paid every year for 8 years. Okay, so we want to know what happens after 8 whole payments. Let's calculate this amount. How much money we will save after 8 years? I'll just write it here a little bit lower. So 9,549.108876. Okay, that's how much money you will have in your account after 8 periods. But still, your next payment is supposed to be a year later. Okay, a year later. But it's interesting to know how much money will you have in that account a year later. Okay, so a year later, this amount will still grow for 1 year. So this amount will accumulate interest over that year. Okay, Let me just erase here, and I'll just write a year later. This 9,549.108876 will accrue interest times 1.05, and it will become 10,026.56. See? So a year later, which is at the end of 9 years, you will have in your account 10,026.56. But remember, the problem asked for $10,000, right? So how many payments are necessary to collect $10,000? So the answer was 9 payments, because 8 whole payments and plus 1 more payment. However, you can already see that last payment is actually negative, right? Minus 26.56. So already after 8 whole payments, just because that interest will also be added over the last year, you will have more money than necessary, right? So strictly speaking, it is enough to have 8 whole payments to get at least that amount, which is $10,000. In your textbook, in problems that you solve for this course, you don't need to worry about that last positive versus negative payment situation. In your problems, you always need just to state how many payments or how many transactions are necessary, okay, to achieve a goal. So, for example, in this problem, you would not have to go into more detail and investigate that last payment. In this problem, your answer will be just 9 payments are required, and more exact answer would be maybe 8 whole payments and 1 partial payment would be required. Okay, so having said that, having spoken about these kind of subtle things surrounding this topic, let's go ahead and check out several more examples which will highlight how we will use these formulas in various situations. In this problem, we are asked how long in years and months will it take to pay off a loan of $15,000 if payments of $500 are made at the end of every month at 3% compounded monthly. So in this problem, that's again ordinary simple annuity, and in this problem we are again asked for a term. But remember, these formulas are giving you answer in terms of number of payments. Okay, so we need to find that first, how many payments are required, and of course these are monthly payments. So after we find how many payments are necessary, we will be able to interpret that result in terms of time. Okay, so don't get confused between payments, a number of payments, and time. Okay, so that's a different thing. So you could have a certain number of payments, but in terms of time, that can be different. We'll see more example about that. So now let's proceed to find this n, and of course that will be this formula for present value, because that loan is a present value here. So n is going to be minus logarithm 1 minus 15,000 times I, okay? And that I is 0.03 divided by 12. Okay, you see? And we divide by payment, which is 500. We'll be dividing that by 1 plus 0.03 divided by 31.22358,114, right? So if I calculate this, that's what I'm getting. So this means that there will be 31 payments, whole payments, and also 1 partial payment required. Okay, so in total there are 32 payments. Okay, so again, this formula gives us the number of payments. So we have 32 payments required. More exactly, again, 31 whole payment and 1 partial payment required. But these are 32 monthly payments. Okay, so now we can interpret this in terms of years and months. This is, of course, 24 months for 2 years, so there are 2 years and 8 months left, right? So it's going to be 32 payments, which means that it's 2 years and 8 months. 2 years and 8 months. So 2 years because 2 years covers 24 months, and also we have 8 more months to cover the remainder here. Okay, so the answer to this problem, it will take 2 years and 8 months to pay off a loan. Now, based on the example that we already talked about before, you realize that you could be asking that question now: is that last payment, could it be like a negative payment? No. When we're talking about present value, or when we're talking about the loan, that effect doesn't happen, that maybe you need last payment negative. In future value that happens, not always. In some cases you have that last payment which may be negative, like a refund kind of thing, or it might not happen in future value. In present value, it never happens. Okay, so that last payment will always be just positive partial payment. But these are the subtleties which really you can think about, and I invite you to think about it deeply, about those subtleties, so that you are aware and also becoming more professional around these problems. But if you want to keep it simple, every time you solve for n, you just need to find the number of payments together with the partial payment, and convert that into time. Okay, so this is ordinary simple annuity. How would the situation change if this was, let's say, a general annuity? Okay, so let me solve the same problem with a general annuity in mind. So let's say I have this compounded daily rate now. So what if this problem was asking about compounded daily rate? So you realize that if it's compounded daily rate, I cannot now use this formula anymore because that's a general annuity, right? And these formulas are based on ordinary simple annuities. So what I need to do just what I did before when I encountered general annuity. That is, I need to convert the rate first. So let me now redo this problem, keeping in mind that this annuity is general. So if that is a general annuity, so we find I2 first, and that will be 1 plus 0.03 divided by 365 over 12, because we want to get monthly rate. So let's see what that is. So it will be 0.002503025. Now, with this converted rate, or with this equivalent rate, we now have simple annuity, so we can use this formula. So this formula now will be just the same kind of process, except that we will have a rate which is I2. So we use I2 as our rate. So let's calculate that. So the answer here is 31.23. 31.23. Okay, which means we have 32 again, 32 payments. Okay. And also this can be translated into time, which is 2 years and 8 months. Okay, so the situation didn't change much because of the change in rate. In terms of answer, the situation didn't change much, but you need to realize that it's not always going to be the case. Okay, so sometimes when the rate change, actual answer can be a little bit different. So just watch out for that. Long story short, if you have a general annuity, you just need to change the rate, and that's it. You solve it with a changed rate because now that annuity becomes a simple annuity. In our next example, I want to demonstrate to you how you would solve these problems if you have a due annuity. Okay? So now, if you have a due annuity, you will need to modify this payment by multiplying by 1 plus I. Okay? Now, there are some subtle things to speak about here. First, let's just try to solve for this problem. So John invests $700 at the beginning of every 3 months at 6% compounded daily. How long? In quarters. In quarters. Will it take him to collect $20,000? Notice that in this problem we are not asked about how many payments, but how many quarters will it take. Well, it will happen that for the future value, the number of quarters in this case and the number of payments will coincide. But okay, first let's just go ahead and solve this problem. So that's a general annuity, therefore we need to start with finding I2 first. So 0.06 divided by 365. 365 divided by 4, right? Because we want quarterly rate, minus 1. So 0.06 divided by 365 plus 1. So it will be 0.015111813. So that's our converted periodic rate. Because that's a future value question, we'll be looking for n, and it will be logarithm 1 plus future value. We are interested, or John is interested to collect $20,000 times I2. So we have the general rate here and PMT. Okay, so $700 is the PMT, which must be modified by multiplying by 1 plus I2 because that's a due annuity, right? It's at the beginning. So then 1 plus I2. Let's solve this. So the answer is 23.63, right? Which means that in this problem there will be 23 whole payments and also a partial payment, which, because it's a future value, which that last partial payment can be some, negative payment. It could be that it's a negative payment, meaning that John will actually overshoot with 23 payments, keeping in mind that last period interest. But it could be also a positive payment would be required if that interest over the last quarter will not be enough to really hit that number. But if I actually, some problems will be having this at least. Some problems will have this at least, phrase here, which will mean that if we want $20,000 or more, then it's okay. We can always safely say that it's going to be 24 positive payments in total. So 24 payments in total will be required here, and if converted into number of quarters, that will be 24 quarters, right? So that the answer for this problem will be 24 quarters. Okay. What I want to do now, I actually want to consider exactly the same problem, but I'll make it a present value problem to show how for due annuities, present value can be a little bit different in terms of interpreting the result, interpreting the answer as time versus the number of payments. So we'll say that John pays $700 at the beginning of every 3 months at 6% compounded daily towards a loan. So let's say towards a loan. How long? So let me remove this at least part one now. So we don't need it anymore. So how long in quarters will it take him to pay off a loan of $20,000? Okay. See, I made this problem different now. I made this problem a problem about present value. So now, instead of collecting money, John is actually paying off a loan. And the question is still the same. How long in quarters? Well, how do we modify the solution? First, I2 will remain the same. What about n? Well, it will change in two ways, right? Because it's a present value problem. So it will be minus, right? So there will be two negative signs here. So 20,000 now is the present value. Still, we have the beginning, right? So the beginning of every 3 months. So therefore, we still keep this multiplication by I2. So let me now calculate the answer here. So the answer I got is 36.93. Now, remember, what is this 36.93? That's 36.93 payments, right? So in other words, we have 37 payments. 37 payments. But in order to understand how many quarters in terms of time are necessary to pay off this loan, we really need to remember something about due annuity. Okay? Now I don't need these formulas anymore, so I can erase that. Let's just remember something about a due annuity. In due annuity, we have payments starting here, times 0, right? So we have $700 payment. Plus first quarter, we have another payment, 700, right? But you know what? I'll not continue now drawing this timeline, because what I want you to notice is that imagine that this answer was not 37 just for a second. Imagine that this answer was just 2. Okay, so what that means is that there are 2 payments required. But how do you interpret those 2 payments in terms of time? Okay, so look, here there are 2 payments are required. That's right, but it's only 1 quarter would be required, right, to cover those that loan. Because look, the first payment is today, right? And the second payment is after 1 quarter. So there are 2 payments, but it's only 1 quarter as in terms of time, how much it will take, only 1 quarter, despite the fact that it's 2 payments. The reason for this is that this annuity is due. And in due annuity, the first payment is happening today. So that first payment, even though it exists, it still doesn't count towards any time, because today is today, right? No time has passed. But ultimately, using the same logic and returning to that result that we got, we have another payment here, so then it will be continuing. So, you know, the last payment, so somewhere plus 35 quarters we have some $700 whole payment, and then there will be partial payment, right? So the last, because remember, this 37 is a rounded up number, right? So this last payment will be partial payment. So let me use P here, okay? So that's not whole $700, it's a partial payment after 36 quarters. But all of them combined represent 37 payments, right? So look, so these all payments are 36 whole payments. So all these are 36 whole payments, and there is also one last partial payment. One partial. One partial payment. So 37 payments in total. But look, because the first payment was made today in this due annuity, actually it is 36 quarters that are necessary, okay, to close this loan. 36 quarters. So John will pay this last partial payment after 36 quarters, and that's it. The loan is paid off. That's because this is a due annuity. So, all this long story short is to demonstrate that when you have a due annuity and when you have a present value that you're talking about, and when you find that result in terms of payments, let's say we in that problem found that it's 37 payments that John must make. So that's, yes, 37 payments, but in terms of time, that's going to be 36 quarters. 36 quarters, so one less period because it is due annuity and because that's a present value of the due annuity, because that's the loan. Okay, so that covers our discussion of finding term for the annuity. Of course, that's a interesting topic with a lot of subtleties, and the only way really to completely understand it is maybe watching this video several times and also solving a lot of problems. Solving a lot of problems, it's the only way to really understand what's happening. So watch this video several times if necessary. Practice these problems. Think deeply about what I said today. Read the textbook, and you should be fine. Okay, and ask your questions during the Q&A classes. Okay, so bye for now. This ends all these classes dedicated to mathematics of finance. Okay, so bye for now.